name is Piotr. I'm working for DataStax company, and we are the company behind Apache Cassandra, building an enterprise version of Cassandra. Actually, it's called DataStax Enterprise Platform, which is integrating Cassandra with search and with various analytics engines. So this talk is going to be not about our commercial offerings. It will be all about open source. We are using Scala for half a year, or a little more now, to integrate, to provide some nice analytical capabilities on top of Cassandra using, quite a hot package right now, which is called Spark. So first, a short introductory slide for anyone who hasn't been using Cassandra or haven't heard about it. So Cassandra is a NoSQL database system that is first fully distributed. It's already distributed hard, as you heard on the keynote. But it is also scalable, which means that you can add many nodes and the performance would scale actually linearly with the number of nodes. One of the biggest, there are a few clusters already over 1,000 nodes each. So Netflix has something, Apple has things like that. The architecture of Cassandra is very simple. There is only one type of node. Everything is symmetric, peer-to-peer. There are no single points of failure. So there's no master slaves, like you have to fail over some master process, and during the failover, your cluster is not responding. Not with Cassandra. It is also optimized for mostly low latency and simple queries, so key-based lookups, small rows. It works in multiple data centers. So you can have one data center in Europe, one in the United States. If even the whole data center goes down, then your application is still operating normally. There is no Scala in Apache Cassandra, unfortunately. Everything is open source. And because it is written in Java, it was also pretty easy to integrate it with Scala frameworks. Okay, so those are good things about Cassandra, and whenever I tell people about the scalability, reliability, they're first extremely impressed, and then they start using it. They try to do a join, they try to do group by, and then they're disappointed. Oh, it's broken, it doesn't work, it can't even process a simple join. It is a database, really? So yeah, to fix this, we integrated with Spark. With Spark, you can put all your data into a Cassandra database and then analyze it with Spark. It supports all the joins, group bys, aggregates, and many other extremely useful features. It's also distributed. It's also scalable. It's reliable, I'd say almost as reliable as Cassandra, but not as much because it's still kind of master-slave architecture. So there's master node and there are worker nodes, and then there's some kind of failover for the master. But it tolerates failures of workers, so even if the worker fails during some computation, then it can move that part of computation to another worker and the job completes. It is implemented mostly in Scala, and the whole core of Spark is written in Scala, but it also provides some APIs for other languages. So there's an API for Python, and there is also something for few Java developers, so there's a Java API. So you also don't need to know any Scala to use it. But of course, the Scala API is, I would say, the most elegant of all those three. It's also open source, so that's why it was easy to integrate. So what we built, we created a connector, a library. This is also written in Scala, a library that connects those two words. And this started first as a side project inside the company, so this wasn't even official plans. And afterwards, it turned out that Spark is very hot. Like we got now about 3 or 4 talks already on Spark during ScalaIO. So everyone got extremely impressed about it, that they need to use it with Cassandra, and that's why we open sourced it. The architecture is quite simple. So you've got a cluster of Cassandra nodes. And on every Cassandra node, on every physical machine, you should install one of the Spark nodes. This is very important to collocate those. So this is shown by those dashed lines. In order to get data locality. So every Spark worker would process just its own portion of data that's in Cassandra. This way, you don't need to move data out of Cassandra, transfer it to the network, and process it somewhere else, and then put it back. The layers architecture is all quite simple, so going from upper side, you launch an application in Spark, you submit it to the cluster, Spark distributes this application, splits it into multiple tasks and distributes the tasks to so-called Spark executors, and every executor invokes some part of your code, which then accesses our Spark Cassandra connector, which then calls through the Java driver to Cassandra and can fetch data out of Cassandra or can write data back to Cassandra. And this happens on every node. Other things, other features supported in the connector is not just loading and writing data, but also all the type conversions. It offers some kind of object mapper, so it's easy to work in Scala. So we wanted to make it idiomatic Scala. It's still not perfect, probably because the project is very young, and there are lots of places where it can be improved. But we didn't want to just wrap a Java driver and to use Java code from Scala with native Java conversions, but we try to provide our own API that fits better in Scala. It's also implemented mostly in Scala, so we have additional Python and Java APIs, but I won't talk about them today. So, two short slides about the data models. So the first thing that we had to figure out how to do is the mapping between different data models. Cassandra is using a table-based data model, basically. So you've got columns with column names. The data is stored in rows. Several rows with the same partitioning key can be stored on a single node, so they form a partition. But Spark has a different model. It is just a collection of objects, and it doesn't define what object is. You can store any item that is, well, serializable. So it can be a Scala tuple, it can be a Scala case class object. What's nice about those collections is that they are immutable, they are serializable, they are also distributed. So if any one of you, probably most of you who already used the collections introduced in Scala 2.9, the parallel ones, they are parallelized on a single machine. And with Spark you get a similar feel, but instead of parallelizing them on a single machine, they are distributed on the whole cluster. So that's why you can have a huge cluster and process massive amounts of data. And of course, the collection does not need to fit into memory, which is also a nice thing. So we can process petabytes of data even on a single node, because it's lazy. The bad thing is that most of those collections do not provide random access, so it's mostly iterating. So how it looks like from the developer's perspective. In order to work with our connector, you just need to first initialize it. It's pretty simple. It's like you just need to follow the procedure that is officially on the Spark website. And the only additional step is, because the creating Spark config and creating Spark context, those are standard Spark setup steps. You need to add the Spark Cassandra connection host property. It can accept, by the way, several hosts, so you can separate them by commas. This is also important for reliability. I said no single points of failure. So if you've got more nodes, it is wise to put more nodes here. And this tells our connector to the nodes to connect to. And then you just take your Cassandra table. For instance, it's in the DB key space, and the table is named tweets. You call Cassandra table on the context, and you get an RTD representing your Cassandra table. Every row of a Cassandra table would be transformed to a Cassandra row object. This is a case class, so it's also serializable, it has all nice properties, so it plays well with the rest of Scala. And then you can do some querying on it. I mean, just not display the whole table, but you can filter. There's a special command where which pushes down the filter predicate down to Cassandra, so the filtering happens actually on the Cassandra side and not on the client side, so it is quite fast and it doesn't need to transfer any data. Then you got you can do of course some mapping, so you can transform every row. For example, extract a column. Here we are extracting a string column called message. And then you can, for example, flat map it, so split every text by white space and generate another collection of words. And finally do a reduce. All of those transformations are lazy, so until I call the last step, collect, for example, they are not computed. They're just remembered. So it creates a pipeline of processing. It's just remembered, but it's not computed until I really want to get the final result. And finally, I will collect. Collect just takes all the data from the result. Okay, so a few words about how we did that. So how it started. In order to provide your own RDD, we just extended the base class RDD in Spark and overrode 3 methods of it. Of course, the Cassandra, full Cassandra RDD has many more methods, but those are mostly private. So it started from three of those. The first one is get partitions. So this is a method that tells Spark how the data is partitioned. It just returns an array of partition. And partition is just some. Here the partition is an abstract class, but we implemented it with the Cassandra partition, which remembers the ranges of data. So this way we can partition the table into several pieces. Then for each partition, we can tell Spark on which hosts. This returns unfortunately a string. This is host name. This should be probably more type safe, but this returns a sequence, a collection of host names. This tells Spark where the data are located so that it can avoid copying the data between nodes. In a perfect world, it would just move the tasks to those nodes containing the data. And finally, the compute method that needs to just return an iterator to the data. So that's why there's no random access yet. The interface between Spark and Cassandra is just pure iteration. Okay, when writing, I won't go into deep details, in technical details. You can see the open source code on the GitHub. I just picked a few things that I found interesting. So there are a few things that we really, really love in Scala. So one of those is basically everything around implicits, implicit type classes. So one thing that is pretty standard pattern for extending library, for extending existing classes with implicits. It is used to add the special Cassandra table function, or the function save to Cassandra that you can call on every Spark RDD. This way, we didn't need to modify any Spark code. So no forks. It just runs with the original Spark, but there are new methods. And another thing, type classes. So they're used for conversions. We all know that every programmer has its own favorite date class. So some of them are forced to use Java util date. Some would say that, oh no, Java time is the only proper way to do this. So this way, we can provide many of those mappings. And you can, of course, plug in your own ones, so you can write an implicit converter and it will also work. We can, as I said, we've got some kind of Pullman's object mapper. So if you want to have every row your Cassandra table represented by a case class object. You just write a case class with the fields of the types corresponding to the types in the table. It supports all the Cassandra types, so even collections. Cassandra supports lists, sets, maps, and you can put use the Scala types. So this is another reason for providing our own Scala layer, so that it supports all the Scala native types, because the Java driver that is below the Scala connector is using the Java types. So if you use the Java driver directly to do that, you would just get some Java collections, and it wouldn't be that convenient to use. You need to, of course, specify the type of the class when requesting Cassandra table, so it would automatically map that to your case class objects. This is something that probably everyone knows. Scala has one of the best collection libraries available everywhere. So the one particular feature that really blew us completely was the ability to flat map on the iterators. So something that for Java code we probably have, well, that wouldn't fit on 3 slides. We just call flat map on iterators because when the connector fetches a whole table, it needs to do that in parts, in splits. So for every table, or even for every task, there are several queries sent to Cassandra, and every query returns a set of results. But then the final result should be just a flat iterator over the data, so the user shouldn't just see that they are fetched in splits. Okay, so as for the object mapper, we are considering in the future to use macros. We haven't been doing this yet, so this is mostly because the documentation is still lacking, and this is a rather experimental feature, so we are a little afraid of changes here. But yeah, the problem with current approach is that we are using reflection, so the old way of doing things like hibernate. But in the future, we could just generate some code in compile time to map all things, and we could therefore detect like missing type converters during compile time. Now it's not supported. You would just compile fine, but you would get an error in runtime. Okay, bad things in Scala. So one thing that we struggled a lot was that reflection primitives in Scala 2.10 are not serializable. And Spark uses serialization for just everything. It serializes tasks to move them to nodes, it serializes data between nodes, it serializes collections, it serializes context. So it's particularly hard because Scala can sometimes put your value into a hidden field, even if it's just a parameter of the constructor. If you, unfortunately, you didn't notice that you are using it in some lambda in a lazy fashion, and then it's converted to a hidden field, and then when serializing it blows up completely when trying to serialize because it's non-serializable. Hopefully, good that is fixed in Scala 2.11. But unfortunately, we can't use 2.11 right now because everything, Spark and the Spark ecosystem is not ready for 2.11. Probably it's going to happen faster in 2.11. It is planned for the next version. But we need to move everything, and we just don't have any resources yet for such a massive project. There are some other minor things, like basically reflection API is pretty hard to use. There are new concepts. Once you grasp all the concepts, it's pretty straightforward. But the documentation is only introductory, so this is actually the same complaint as with macros. It is introductory. There are introductory tutorials for this, so you are excited. Whoa, macros are so cool! And then afterwards, you try to do real things with this, and oh no, Google doesn't know anything about it. And so this needs to be improved, and I hope it will. Existential types, we run into many things with compiler not being smart enough, even rejecting valid programs, so we have to resort to some typecasting, and we find it ugly. And implicit search, I think this is the typical complaint of anyone new to implicits, that at some point they are hard to prioritize, and all those ambiguities. The system is quite complex in this way. Okay, thank you. So you can find more documentation here on those sites. Any questions? how long to create this project? So this project actually started last year. I'd say that was about 10 months ago. But at first it was just a side project created by 2 developers. And the full development time, I mean, the more people are working on it since I would say good half of a year. So it was released in the, so you can find this in the release of PSE 4.5. And of course it's on the GitHub. So we've got just one stable release so far, and we're currently working on the second one. Okay, thank you very much.
Thank you.